That's a good joke. Okay, here we go. We've got 5 topics, and you'll test on it. Awesome stuff. We start with applications of the derivative. Applications of the derivative. Super cool stuff. Maximums and minimums. You already know what they are. A critical number of a function f is a number c in the domain of f such that either f prime of x is equal to 0. I'm sorry, f prime of c is equal to 0. Or f prime of c does not exist. The beginning of optimization, curve sketching, everything that's important to curves begins with this idea of a critical number. A critical number is any number in the domain. So if you look here, C1, C2, 3, 4, 5, 6, any of these values all the way across the x-axis where the derivative is equal to 0 or the derivative does not exist. Can somebody tell me a place where the derivative does not exist? Why does it not exist at C3? It is continuous, but it's a corner. Exactly. So as you look at this graph right here, we have this spot. It's an endpoint. You can't take the derivative at an endpoint. Here, the derivative is equal to 0. Those are the most common ones. Here, we have a corner. That becomes an issue. We have another spot where the derivative is equal to 0. We have another spot where the derivative is equal to 0. And then we have, again, that corner value. We like to talk about absolute maximums and minimums and local maximums and minimums. The absolute maximum or the global maximum is the largest value over the entire graph. Who can tell me where is the spot where you achieve the largest value? Yep, and when we say absolute maximum, we're referring to the y value. So I'm going to write this as f of c sub 4. So when you plug in c sub 4, that's going to give you the largest value on the graph. What's going to produce the smallest value on the graph? F of c sub 1. Then we have local maximums and local minimums. Local maximum is the largest value in the immediate region. So if you can ever kind of just focus on a general region and say, hey, that's bigger than everything else right around it, then it's referred to as a local maximum. So f of c sub 2 is a local maximum. Can you tell me another local maximum? F of c sub 4. Notice that f of c sub 4 is an absolute maximum and a local maximum. You see how it's both? Yep. Yeah. If you look at the value and if it's bigger or smaller than everything immediately around it, okay? Now, some people don't like that statement, immediately around it, like how close does it have to be? Well, there's a lot of different graphs that you could examine. So, for example, if I draw this graph, it's got a lot of local maximums and minimums, right? Yeah, exactly. Whereas this one, we would say just has 2 local maximums or minimums, right? So if you can, really hone in on just, that small region, say, oh yeah, it's bigger or smaller than everything else in that immediate region, then it's a local max or local min. So we can't say, well, within like 1 unit or within a half a unit or within a tenth of a unit. Just, everything immediately around it. Okay? Small window. Local minimums, yes. Excellent point. The endpoints may not be considered local maxes or local mins. They may only be considered absolute maximums or absolute minimums because it does not have anything on the other side. So we would say we want to say everything immediately around it. It has nothing off to the right or the left of it. So we do not consider those local. You're not dumb. So the local minimum is, you can see right here, f of c sub 3. That's going to be a local minimum. What's the other spot I have a local minimum? Yep. Example 1 says, look at the graph provided, identify. Well, we could go back. I'm not sure what you're asking. I'm sorry. Can we come back? Do you want to pursue it? No. Okay. All right. It says identify the absolute maximum and minimum values as well as the local max and local min. We just did that. A very famous mathematician who we won't get into why he was famous, but for Mott, he says if f of x has a local maximum or minimum at c, and if f prime of c exists, then f prime of c is equal to 0. So what that tells us is that local maximums and minimums, generally always exist at where f prime of c is equal to 0. Just got to make sure you can take the derivative at that spot. Okay? So let's talk about some critical numbers. Examples of critical points. Those are the most common examples that you're going to see of critical points. Okay? And the reason why is because when you take the derivative and set it equal to 0, you're going to find those spots. Okay? Let's consider something else. True or false? That graph has a local minimum. True. True or false? This graph does not have a derivative at the local minimum. True. Yep. It's possible to have a local minimum, but not have a derivative exist there. Why does this not have a derivative? Yeah, because it has a corner. I suppose you end up with that graph. You don't really have a spot where the derivative is equal to 0, but you have a spot where the derivative is, yeah, it's a vertical tangent, right? And so we would say that the slope is undefined. And so we would say that that is critical. Doesn't have a local max, doesn't have a local min at that spot, but it's something we have to take into consideration. This last one, I want you to be careful with it because it's going to try to clarify any points of confusion we have about critical numbers. This is the reciprocal function y is equal to 1 over x. Would you agree that the function y equals 1 over x is discontinuous at x equals 0? Would you agree that if I took the derivative at that spot, that the derivative does not exist as well? So this is technically not a critical point. And the reason why is because 0 isn't even part of the original domain. Okay? You understand that? Like all of these other values, you could plug x in at these spots and produce a value. But if you plug in 0 into the beginning, you don't get anything, do you? So therefore, it's technically not a critical point because it's not part of the domain to begin with. It's a very slight nuance to the definition. It's really not going to be that important as we move forward. I just want you to understand as things pop up in the answer keys, okay? All right. All right. Find the critical numbers of the function. Confirm that the critical number, confirm the critical numbers by sketching a graph of the function. F of x is equal to x cubed minus 2x squared plus x. Take the derivative. Find where it's either equal to 0 or where the derivative does not exist. What is the derivative? I set that equal to 0. Does that factor? It does. 3x minus 1 and x minus 1. Is that right? So therefore, we have x equals positive 1/3 and positive 1. Take out your calculator. We'd like to confirm that there are critical numbers at those spots by examining the graph. So I take out my calculator and I type in x cubed minus 2x squared plus x. Zoom 6. Kind of tough to see what's happening right there, isn't it? I'm just going to go ahead and change my window so I can kind of see that area right there. I bet if I do an x value of negative 1 and an x max of positive 3, that will show everything I need to see. And a y minimum of negative 2 and a y max of positive 2. I bet I'll see what I want to now. Okay. Can you see the local max and the local min? It was tough until we zoomed in, wasn't it? But is there a local max and local min? It's very subtle, but it's there. So it confirms that we have a local max and a local min. If you simply did your trace, you could approximate that it looks like you have a local min at 1. And then if you go back here, looks like we have a local max at about, 1/3. Yeah, 0.36, 0.31. I bet if we zoomed in, we could be right at 0.33. And we could even do second calculate maximum minimum and see if it comes up with that, couldn't we? Yeah. But are you convinced? Okay, let's move on. The next one. Oh boy. Yes. Nope. Oh, by sketching a graph, sure. There we go. Yeah. We looked at it and we saw that at 1/3 and at 1 that there was a local max and local min. Again, this is for you. This is a way to check your answer. How would you do it? Look at the graph. It should show up. If it doesn't, something's wrong. Next one. What rule would you have to use? Take this derivative. Quotient. Or let's make life easy. I'm just going to divide through by x, and I get x minus 1 over x. Those are the same, aren't they? Wouldn't you much rather take the derivative of this one as opposed to the derivative of this one? If you want to do this one, do the quotient rule, go ahead. But I'd like to do that one instead. First of all, are there any values of this where the derivative does not exist? 0. Why? Yep, it's undefined at 0. Would you agree that the domain for this graph is x cannot be equal to 0? Okay? So we should see that same thing pop up in the derivative. We won't have a critical number there because it's not actually part of the domain, but it should pop up. F prime of x. What's the derivative of x? 1. And what is the derivative of negative 1 over x? Plus 1 over x squared. All right. So Can you see where is the derivative undefined? For what value? 0. That's what we anticipated as well, right? 0 is not part of the original domain, so we're not going to call it a critical value. I'm going to set this equal to 0 and solve. Now, over the years, I've learned that it is very helpful in this situation to just create one fraction. 1 plus 1 over x squared. I'm going to create common denominators. What should I multiply the top and bottom by? X squared plus 1 over x squared, right? Does x squared plus 1 factor? No, it does not. Could this ever be equal to 0? Could the top ever be equal to 0? No, it couldn't. So I'm going to say that there are no critical numbers. I don't know about you guys, but I'm worried by that result. How could I check it? Let's look at the graph and see if the graph confirms that there are no critical values. Parentheses, x squared minus 1 divided by x. And I will zoom 6. Is the derivative ever equal to 0? No, it's not. And the only spot where the graph does not have a value is at x equals 0, which we anticipated. Yeah, I agree. What does that graph look like? Yeah, it's got the V. Very good. Yeah. In fact, has a horizontal shift of 2, doesn't it? Do you agree? What would you plug in to make 0 here? 2. Absolute value graph. It does have a critical number. At where? At 2. Does the graph confirm that? It sure does. Let's look at the last one. I'm going to rewrite this so I don't have radicals. This would be x to what power? 3 halves minus 2x to the 1 half. Okay. F prime of x. I'm going to take the derivative. What is the derivative of x to the 3 halves? The 1 half minus x to the negative 1 half. Dump the 1 half in front. The 2 goes away. Okay with that? I'm going to choose to write it as radicals now that I've taken the derivative. F prime of x is equal to, looks like 3 roots of x over 2 minus 1 over the root of x. By looking at it, is there a spot where the derivative does not exist? What? Yep, looks like x equals 0 is going to be a critical value. Let's look back at our original function. Are you allowed to plug in 0 for square roots? Yeah, we are. So 0 is part of the original domain, but it comes up as a value we can't plug into the derivative. So therefore, x equals 0 is a critical value. I also have to consider where this is equal to 0. Now, if I want to find where that's equal to 0, I should really find common denominators. What is the common denominator? So I have to multiply top and bottom here by 2, and top and bottom here by root of x. And when I do that, I get 3x minus 2 over 2 roots of x. So we already determined what would produce 0 in the denominator. What produces 0 in the denominator? 0. What produces 0 in the numerator? 2/3. And again, these are kind of challenging to think about. It's telling me that I either can't take the derivative at 0 or I get a derivative of 0, and same thing at 2/3. And so to try to confirm my answer, I'm going to look at the graph. I'm going to look at x raised to the 3/2 power minus 2x raised to the 1/2 power. Zoom 6. Does it look like you might not be able to take the derivative at 0? And if you take the derivative 2/3, you get 0? Let's zoom as a box and see even better. And you'll see how smart the calculus is. Are you convinced by that graph that 0 would be an endpoint of the function? I can't take the derivative of an endpoint, can I? And your graph found that. Furthermore, does this look like it happens at about 2/3? Yeah, and that's where you have a local minimum. Exactly. So your goal today is to be able to take the derivative, find where it's undefined, and find where it's equal to 0. These are 4 good examples for you. You do not have a book assignment today because you never do. You got